Okay, very welcome, ladies and gentlemen, to our next session in the Fractal Seminar. And today's speaker is Jian-Ci Xiao. Did I pronounce it correctly?
Yeah, right.
Thank you, from Nanjing University. And he will talk about similitude embeddings of self-similar sets and self-affine carpets. Please.
Thank you very much for your nice introduction. And of course, this is a great pleasure of mine speaking here. And actually, this is my second time visiting BME, and I should thank Professor Kari Shimon and Professor Balashbarani for your very, very nice hospitality. And today I'm going to talk about the similitudes, the embeddings of self-similar sets and self-affine carpets. Okay, so let us talk a little bit about the motivation. A similitude on the Euclidean space is just a simple map which sends a point x to lambda capital O times s plus t. And here lambda stands for the similarity ratio of that mapping, and capital O is just a d by d orthogonal matrix, and t is just the translation vector. So in particular, a similitude sends a set K into a scaled copy of itself. And for convenience, we will call a similitude F a self-embedding similitude of a particular set capital K if the map just sends K into itself. So in other words, it embeds the set K into itself. So for example, this is a very particular example where K is just the unit square, and here the blue part is an illustration of a self-embedding of the square. And as you can see, when K is as nice as a polygon, actually we cannot say too much about the self-embedding similitude of that polygon, because the restrictions on those similitudes are very, very weak. But when the set K is as irregular as a typical fractal set, you know, a typical fractal set always possesses a strong porosity, and there are many, many holes inside its boundary, and this often imposes very strong constraints on those self-embedding similitudes that the self-similar set admits. To move on, let us introduce some which are very, very commonly used notation. So the first one is we always fixed a self-similar iterated function system, which I denoted by capital phi. And this system consists of m different similitudes, which are denoted by phi sub I. And I just write Ri to be the contraction ratio, capital Oi to be the orthogonal part, and T sub I to be the translation vector. And we will also use capital K to be the similar set associated with this iterated function system. And capital lambda stands for the alphabet, and the lambda star is just a selection of all of those finite words. And as usual, for a bold I, which is a finite word, we just use phi sub I to be the composition of those mappings. And the last one is we always call a set which has the form phi sub I of K to be a self of K. So the self-similar set K is just a finite union of its cells. Here, let me introduce some simple examples of those self-embedding similitudes of a self-similar set. For example, the very trivial one is just phi sub I, which sends K into an exactly self of itself. But as I mentioned earlier, when K has an empty interior, we can not say actually too much about those similitudes embeddings of K, because that interior, because for example, K contains a solid ball in the Euclidean space, and we have not too much restrictions on the no matter the contraction ratio or the orthogonal part or even translation vector about those similitudes embeddings. So usually we will put some nice separation condition on the iterated function system to make the problem interesting. So before stating a pioneering result, let us ask ourselves a simple question. Can the embedded image of a self-similar set K be not exactly one cell, but a finite union of two or more cells of that self-similar set? And the answer is true. And this is a very nice example given by Martin Adikash, Thomas Kelty here, and Andrew Massey. So the system consists of 4 maps. We use the unit interval to do the iteration. And here the number stands for the length of that interval. So we have 4 maps here. This is the first one with contraction ratio 1/6, and this is the second one. This is the third one, and this is the last one. Here the key is that the largest gap has length 1/4, but the smallest gap has length 1/24. So the key is that if you multiply 1/4 by 1/6, then you get exactly 1/24. So in particular, after one iteration, you see here we get a 1/6 contracted copy of the self-similar set here. And it maps the largest gap onto this smallest gap. So here, this is a scaled copy of the whole self-similar set, but it is definitely not a particular cell of the self-similar set, but a union of 4 small cells. A pioneer result was conducted by De Junfeng and Yang Wang in 2009. They actually worked on the real line, that is when d equals 1. And they put the open set condition on the self-similar iterated function system, and they require that such a system is the so-called homogeneous system. That means the contraction ratio of all similitudes in that system is a common value, which I denote by R. So in this case, if F is a self-embedding similitude of K, and if we denote by R sub F to be the contraction ratio of F, then what can we get? If the Hausdorff dimension of the self-similar set is not full, then the contraction ratio of any self-embedding similitude of that self-similar set should be a rational power of the common ratio in that system. So this tells us that usually you cannot embed a self-similar set into itself using a completely new scale. That scale must be already encoded in the system. Oh, sorry. And under some mild conditions, even if the self-similar set has full dimension, you can also get such a, which is usually called the logarithmic commensurability statement. Okay, so this might be one of the first results toward this direction. So since they work on the real line, it is natural to ask whether this statement can be extended to higher dimensional cases. And this was conducted by, again, Adikash, Kelty, and Massey in 2010. But they paid a little bit price. They replaced the open set condition by a stronger separation condition called the strong separation condition. And in this case, in all dimensions, they actually proved that if we write S to be the Hausdorff dimension of K, and again, RF to be the similarity ratio of F, where F is simply a then if F happens to be a self-embedding similitude of the self-similar set, we still have the logarithmic commensurability. That is, the log of the contraction ratio of F should be a rational linear combination of those log of contraction ratios in the original system. So in particular, if the original IFS is homogeneous, then all of this Ri is a common R. And in that case, Rf should be a rational power of that ratio R. And except that this, they also proved a very nice statement, which is if f of k is just a scaled copy of k. So if this scaled copy of k intersect the original self-similar set k in a very large part, that means the intersection has positive S-dimensional Hausdorff measure. This is actually equivalent to say that the scaled copy contains the cell of k. So in a local area, the scaled copy f of k and k coincide in that area. As you can see from the right-hand side to the left-hand side is trivial. For if f of k contains a cell of k, then that intersection set already contains a cell of k, which of course has positive Hausdorff measure. So the non-trivial part is how we move from the left-hand side to the right-hand side. So again, it's natural to ask whether we can remove this separation condition or at least relax it. And I'm sorry. Together with Guirao, we actually proved that both of these statements, these two statements remain valid when we only assume that the iterative function system satisfies the open set condition instead of the strong separation condition, but we require the self-similar set to be totally disconnected. Of course, if K is not totally disconnected, for example, if it contains an interior point of the Euclidean space, then of course, at least the first statement does not hold. But there is a possibility that even if K is not totally disconnected, or even if it is connected, but it has a Hausdorff dimension strictly less than D, then these two statements might also hold, but we just don't know how to prove it. So this is about how we embed a self-similar set into itself. Like this, make this appear. Okay. So furthermore, assuming the strong separation condition, Alikash, Kelly, and Massey actually proved a more. That is, they proved that actually almost all points in the embedded image are relatively interior points. I mean, with respect to K itself. So the whole space is just the self-similar K instead of the Euclidean space. So almost all points are relatively interior points. And another observation is in all the previous examples, the embedded image is simply a finite union of cells. So this leads to a very natural question that under the strong separation condition, if F is a self-embedding similitude of K, must the embedded image be simply a finite union of cells of K? I mean, whether or not there must be, this must be the case. Let me make a simple remark here. So it is equivalent to say that the f of k is a finite union of cells of k, then to say that f of k is relatively open in k. And this is very easy to show. And later I will choose only this expression because it is shorter than the than that hand side. Okay. So due to the time constraint, I will not go into details about this statement. So in 2024, I proved that under the strong separation condition, if all the similitudes in the original IFS share a common linear part, I mean that they have the same contraction ratio and they have the same orthogonal matrix, then under this strong condition, the embedded image must be a finite union of cells of K. But this is almost optimal. If you allow the orthogonal parts to vary, I mean, the contraction ratio can still be the same, but if you allow the orthogonal parts to be different, then the embedded image need not to be a finite union of cells of K. And let me give you an illustration of the counterexample. So here, my system consists of 9 mappings, and all of them has the same contraction ratio, which I cannot remember explicitly, but maybe 1/6. And here we have an island, and here we have these 4, and on the right corner we have these 4. So for the red arc, I mean the orthogonal part is a counterclockwise rotation by 90 degrees, and this is clockwise rotations by 180, and this is just 270. And the right corner part is exactly the same as the left one. So they are just replicas of each other. And here we have an island, and after several iterations, the subsimilar set looks like this. So the embedding is just maps the whole subsimilar set into this particular part. So let us do some colorful things. If we colored this island by red, and this left corner part by blue, and this right corner part by green, then here we show an illustration of the embedding. So the embedding will map the whole blue part here. And not only the square coincide, but the counterset inside it are exactly the same. And it maps the green part here. And the tricky one is to map the red part here in the middle of these 4. And after some iterations, it is not very too hard to see that the fixed point of this red map is not an interior point of the embedded image. So this is actually quite closely related to a problem on the generating IFS, which was perhaps were posed by several people, experts in the field of fractal geometry, like Urbanski or Cousin Lau, Jun-Jason Law, in, I don't know, 2012 or even earlier. They asked a very fundamental question. Are there 2 self-similar iterated function systems on the Euclidean space which actually generate the same attractor? But one of these systems satisfies the open set condition, but not the strong separation condition, while the other satisfies the strong separation condition. So for example, we have in hand a subsimilar set of which a generating IFS of it satisfies the strong separation condition. And we are which satisfies the open set condition, but not the strong separation condition. And it is very nice if we can just find another generating system of it, which actually satisfies the strong separation condition. You know, strong separation condition is a little bit nicer than this condition. A very special case is to look at this subsimilar set, which is called the 145 set. So here we use the unit interval to do the iteration, and the system consists of 3 maps. The first one is this, the second one is this, and the third one is this. And all of the contraction ratios is just 1/this. But this very natural generating iterative function system of this subsimilar set, of course, it satisfies the open set condition because 0, 1 is just a feasible open set of that. But the second copy and the third copy actually has an empty intersection. And here is the intersection point. So they asked whether you can find a new generating system of this subsimilar set, which actually eliminate this intersection. That is, it actually satisfies the strong separation condition. And this is no. The answer is negative, and this was proved by De Junfeng and Hu Junren several years ago.
Sorry, this is a negative answer to the special case or the general question?
The special case, a very, very special case of this one. So actually, they proved a much stronger statement than this case. So this is their result. In 2023, they show that if we assume the original system, which is phi again, is homogeneous, that again, this means that all contraction ratios Ri is just a common value R. And if the system actually satisfies the open set condition, but not the strong separation condition, then you can never find another self-similar generating IFS of this set, which satisfies the strong separation condition. So the intersection is an, what can I say, intrinsic property of this self-similar set. But as you can see, they also need the homogeneity assumption here. In the inhomogeneity case, there is an essential obstacle. So why does these two problems being, closely related? So here is the relationship. For a particular self-similar set K, if you can prove that the strong separation condition together with the self-embedding actually implies that the embedded image is open, then the above statement holds, even without the homogeneity assumption. I mean, for a particular case, if you can show that it satisfies the strong separation condition and all of its self-embedding images are relatively open, then you can never find a self-similar set, a generating self-similar subset of it satisfies a weaker separation condition. And the proof is very simple but interesting, so I maybe go into details it. Suppose phi satisfies the open set condition but not the strong separation condition. So this is the original generating iterative function system of K. The question is, can we find another iterative function system of K satisfying the SSC instead of the OS? So since the original system fails this strong separation condition, there are two copies which has an empty intersection, right? There must be, because otherwise the system already satisfies the strong separation condition. But if in a perfect world you can find another iterative function system of this particular self-similar set with the strong separation condition, then you can regard this self-similar set as a set with a stronger separation condition. And you regard these two copies as two self-embedding images of the self-similar set. So these are not selves of that self-similar set, but just embedded image. But if this statement is true, I mean this implication is true, then these two sets, which are just self-embedding similitude in images of K, then both of them should be relatively open in K. And since both of them are open subset of K, their intersection should be an open subset of K. But they have an empty intersection. So the intersection actually contains a cell of K. But since it contains a cell of K, it of course has positive Hausdorff measure. But we all know that the open set condition denies this. The intersection of these two copies should have zero Hausdorff measure, and we get a contradiction. Okay. So as you can see, these two problems, the embedding problem and the generating iterative function system problem, are closely related to each other. And this statement is a little bit stronger than that. Okay, so up until now, I only talk about the self-embedding similitudes from one particular self-similar set into itself. So what about the embedding between different self-similar sets? We already have in hand a self-similar set, which is K, and now we fix another one, and we let psi to be another self-similar iterated function system, and let capital F to be the associate attractor. Here I use lambda j to denote the contraction ratio of this new system, and qj to be the orthogonal part, and a sub j to be the translation part. And you can actually ignore this one because we will never use it. A very maybe direct corollary of our result is that assume both of these systems satisfies the open set condition, and again, both of the attractors are totally disconnected, then if they actually have the same Hausdorff dimension, then this very nice statement of electricality and Massey still holds in this case. That is, if F and K has a very large intersection, which in the sense that it has positive S-dimensional Hausdorff measure, then you can actually prove that the intersection contains a self of one another. So this largeness will imply a topological largeness. Okay. Of course, this requires them to have the same Hausdorff dimension, because otherwise the left-hand side does not fold. Okay. And besides of this, there is a very famous conjecture posed by De Junfeng, Wen Huang, and Hui Rao maybe over a decade ago. Their conjecture is, suppose these two self-similar sets are totally disconnected. Maybe they satisfy the open set condition, maybe even the strong separation condition, it doesn't matter. But if one of the contraction ratios in the second system is not a rational linear combination of the logarithm of ratios in the first system, that is the roughly speaking, the logarithmic commensurability does not hold, then you can never finally embed the second one into the first one. So this represents some algebraic intrinsic properties between the subsimilar sets if one can embed one into another one. Not only using similitudes, but even non-degenerate affine maps. And this is this turns out to be a very, very difficult problem. Here, let me show you some partial progress towards this problem. So we always assume that they are totally disconnected. And in their original paper in 2014, they proved this conjecture when the first system is homogeneous with the strong separation condition, and the Hausdorff dimension of the self-similar set is strictly less than 1/2. In this case, the conjecture is true. In 2019, Pablo Schmerkin and Meng Wu proved independently that the conjecture is true in the one-dimensional case, but they also require the system to be homogeneous with the open set condition. And of course, they should have strictly less dimension strictly less than 1. And in a very recent preprint, Amir Alban, Michael Hoffman, and Meng Wu, they proved this conjecture when both of these systems satisfy the strong separation condition, and all contraction ratios involved are algebraic numbers. And in this case, the conjecture is true. There are also many partial progress which I will not go into details, like Algam 2018, Feng Xun, and 2018, Algam and Simon Baker. A very, very special class can be regarded as a very direct consequence of our previous result. That is, if both of these systems satisfies the open set condition, and the two self-similar sets share a common Hausdorff dimension, then you can never embed one into another using not affine maps but similitudes if the logarithmic commensurability does not hold. At least on the real line, there's no difference between similitudes and affine maps, and the real assumption is this very strong coincidence of between their Hausdorff dimension part. It would be very nice if for example, the Hausdorff dimension of K is strictly less than the Hausdorff dimension of F, and if you can embed K into F, maybe you can find a nice subsystem of F which has Hausdorff dimension exactly the dimension of K, or even a translation of that subsystem, but this seems to be quite hard to prove. Okay. So until now, I'm talking about embedding between self-similar sets. What about the self-affine case? For general self-affine sets, this problem seems very hard, very, very hard, but it's good to have some, geometric structure inside the self-affine sets to make some real progress. So a very nice test example is the so-called Bedford-McMullen copy, because it possesses very nice grid structure. So we all know that a Bedford-McMullen copy can be determined by 3 parameters. The first one is n, which is strictly larger than m, and the alphabet is just capital lambda, which represents the initial pattern that we chose. And to avoid trivial exceptions, we always assume that we choose at least 2 sub-rectangles, but not the whole of them. So in this case, the copy is just a singleton. And in this case, it is just a unit square, and there is nothing particularly interesting. And we will denote the self-affine copied by K, and it looks like this. Okay, so here we have an example of the Bedford-McMullen copy. As we can see, I myself prefer this n to be strictly larger than m, so the copy actually stands instead of lie down. And so we are looking at very, very thin, long, thin rectangles which are standing up. So here, n is equal to 3, and m is just 2, and the capital lambda is this. The position, this one is 0, 0, and this is 1, 1, and this is 2, 0. And after several iterations, you get something like this. So the question is, can we embed this copy into itself using some nice similitudes? For convenience, I would like to introduce the notion of obliqueness. I will call a line in the plane oblique if it is not parallel to one of the principal coordinate axes. So literally, it is an oblique line. And I will call a similitude F oblique if the similitude sends the x-axis to an oblique line. So it kind of involves some genuine rotation. So in 2019, Algam and Hockman, they proved that if K is a Bedford-McMullen copy, this is what we call the independent assumption. That is, n is not a rational power of m. The 2 ratios determine that copy is not this one. And later, from now on, I will always refer to this condition as, independent assumption. So except some trivial exceptions, every self-embedding similitude of this copy, which is assumed, which the independent assumption is assumed, every such similitude should be a non-oblique isometry. That is, the self-embedding should not be oblique. It will send the x-axis to either a line parallel to x-axis or y-axis, and even more, the similarity ratio should be 1. You cannot actually contract the original copy into the cell. And to give some intuitions, the first one they use is the projection theorem given by Ferguson, Jordan, and Schmerkin over a decade ago. That is, under the independent assumption, for every oblique line, the orthogonal projection of the carpet onto that line has Hausdorff dimension exactly the minimum of 1 and the Hausdorff dimension of k. So this is just a Mastrand's typical value. And the key is that they prove this for every oblique line instead of just typical ones. So how will this projection theorem help us to deny some oblique self-embeddings of the carpet? For example, if the projection of the carpet onto one of the principal axes has dimensions strictly less than this value, then of course the carpet cannot admit oblique self-embeddings, because an oblique self-embedding will rotate the carpet. So for example, the f of k inside it, the projection of that embedded image onto the x-axis is actually the projection of the original one onto an oblique line, at least a scaled copy of that one. So there will be a gap between these two dimensions, and we will get a contradiction. The second one is something like the one-dimensional logarithmic commensurability statements, not only for self-similar sets, but for horizontal slices or vertical slices or tangent sets. And roughly speaking, how would this help us? I mean, if F is a non-oblique, first we always prove that the self-embedding is non-oblique, and then we prove the logarithmic commensurability. So if we have already proved the non-obliqueness statement, then we can actually divide the question into two cases. The first one is, since it's not oblique, it will map horizontal slices into horizontal slices. But this one tells us that since we have some one-dimensional commensurability here, and the embedding maps horizontal slices into horizontal slices, then looking at some particular horizontal slices, we can actually show that the contraction ratio of that embedding map is a rational power of n. And since it maps vertical slices into vertical slices, by looking at some particular slice, vertical slice, we can show that the contraction ratio of f is actually a rational power of n. So both of these commensurability holds simultaneously. But we know that n and m are independent. They are not a rational power of each other. So there is only one case, that is, the contraction ratio is nothing but 1. Okay, so this is where the independent assumption of n and m plays its role, but in a very rough way. And if f maps a horizontal slice into vertical ones, then this is actually impossible because n and m are independent. So you actually maps something like a m counter set into an n counter set, and this is this turns out to be impossible. So this is how a very, very rough way how we consider the embedding problem of self-affine copies. So it is quite natural to ask whether we can say something in the dependent case, that is when n and m are rational powers of each other. So last year I note that, again, some trivial exceptions aside, every self-embedding similitudes of such a carpet in the dependent case should again be non-oblique. So it should again involve no genuine rotations or reflections. But of course, in this case, we cannot prove that the similarity ratio should be 1 because such a carpet can be a self-similar carpet, and there are many, many self-embedding of it which has similarity ratio strictly less than 1. But at least the similarity ratio of the embedding map is a rational power of n, also a rational power of n. How much time do I have? Sorry.
10 minutes.
10 minutes. Okay. So since we have some time, maybe I can give a very rough sketch of the proof for the non-obliquities result, because the second one, I think, although we use different languages and maybe different methods, but in the very essential sense, they should be the same with algorithm and cosines. And the key is to prove that first that such a self-embedding should be non-oblique. Roughly speaking, I divided into two cases. The first one is when the carpet contains no vacant rows. I mean, every row there is a selected, at least one selected rectangles. So the first step, I show that such a carpet never contains an oblique line segment. This is very strange because in the self-similar case, there are some cases where the carpet contains oblique line segments. So for a self-affine carpet, it never does. So if there is a full row, then the conclusion follows immediately. We can never contain an oblique line. So the carpet never admits an oblique self-embedding. But if there are no full rows, a suitable rescaling of a local part of the embedded image will yield a contradiction whenever the embedding is oblique. Well, very roughly speaking, since K are consisting of very thin rectangles, and if you embedded a very thin rectangle into itself, that one will contradict the grid structure very locally to that carpet. The second case is when there exists a vacant row, so the projection onto the y-axis is a real deleted digit set or a Cantor set. And the first step is to establish a logarithmic commensurability theorem for not only deleted digit set, which was already obtained by De Junfeng and Yang Meng, but for generalized one, for example, a large horizontal or vertical slices of it, which can be regarded as some Moran constructions. And in this case, if the carpet admits an oblique self-embedding, then it turns out that we can change the question a little bit. We can find an oblique embedding such that G of K is contained in some, maybe we can regard this as a tangent set of the carpet. That is a counter set, the product of the counter set with the real line. And in this case, with some additional work on the one-dimensional embedding problem, I mean, we not only we have to analyze how the contraction ratio acts, but how special the translation vector is. And with some additional work like this, we can actually find a contradiction in this case. So this is my result on the self-embedding problem of self-affine copies. And in the end, I would like to mention again a relationship with an open slicing problem of self-affine copies. To the best knowledge of me, this is still open. The problem is, if in the independent case, do we have for all oblique slices of the carpet has Hausdorff dimension at the most, the maximum of the Hausdorff dimension of the carpet itself -1 and 0. Again, this is the value given by Mastrand's slicing theorem. And they wonder whether or not in the independent case, all vertical slices has such a upper bound. So where does this relationship lies? Let capital N to be the maximum number of selected rectangles in any row. So this is the largest number where we select a rectangle in some particular row. And it is easy to find a horizontal line with Hausdorff dimension exactly log of capital N divided by log of N. So we just look at the fixed point of that row. So if K has non-uniform fibers, that means there are at least two rows which contain a different number of selected, no, not squares, but rectangles. Then using the formula, it is easy to calculate that such a upper bound is strictly less than log of capital N divided by log of N. So in this case, if you can actually find an oblique self-embedding similitudes of K, then such an oblique embedding will send this horizontal slice to an oblique one. Yeah, but if this conjecture is, or this inequality is true, then an oblique slice has Hausdorff dimension strictly less than the horizontal one. And you will get a contradiction. You cannot never embed a large set into a small set. So this is the relationship. It does not exclude all cases, but at least it tells us many things. At least in the non-uniform fiber case, because in the uniform fiber case, the carpet is Alpha's regular set, and maybe it's simpler in that case. So there are actually some partial progress toward this slicing problem. The first one is again proved by Schmerkin and Wu independently in 2019. So this problem is true when K has the product form. That is, it is the Cartesian product of two Cantor sets. And 1 year later, Amir Algam showed that every oblique slices has upper box dimension strictly less than this value. So the difference is just that he replaced the Hausdorff dimension of K by the star dimension of K, which was introduced by Furstenberg himself, but I believe in this case, it coincided with the Oswald dimension. And as we mentioned earlier, if K has uniform horizontal fibers, then it is a regular set, and all of these dimensions are the same value. So in particular, it has the same Hausdorff dimension and Oswald dimension, so the two upper bounds coincide with each other. But in general, the Hausdorff dimension is strictly less than such a star dimension. So the upper bound provided by Algam is a little bit larger than the expected one. But several years later, together with Meng Wu, they actually refined such an result. They proved that every oblique slices of the carpet has Hausdorff dimensions strictly less than this one. So this is the Hausdorff dimension of K minus a value which is at the most 1. And this value can be obtained by this upper bound just multiplied by such a fraction, and you will get this. So this is a refinement of this one, but it is still, there's still some gap between this upper bound and the expected one. Okay, I think I should stop here. Thank you very much.
Thank you very much. Questions, comments?
Yeah, I have two questions. You mentioned a corollary about referring to the first result when there were two different, and it was a corollary of what?
Of this. Sorry, it takes some time to go back. I mean this one.
No, you mentioned a corollary.
Yeah, it is
it's a corollary of that.
Of this, because this is we consider f of k intersect k, right? Mm-hmm. But in that corollary, we consider the intersection of a different subsystem set together with k. So using some rescaling argument, you can actually reduce that problem into this one, this self intersection case, and then everything can be done.
Okay, and my other question is about this theorem. So, mm-hmm. So can you say anything about the proof, or what are the new ingredients?
I mean, the proof is in some sense analogous to the proof of yourself. But we just discovered that the open set condition together with the totally disconnectedness is not too far away from the strong separation condition. And there will be some tricks involved. The proof is a little bit trickier than yours, but I think in the very essential sense, they are the same.
As far as I remember, for us, it was important there was some
Yeah.
So do you also have the gap result?
Yeah, we have the gap. The gap result was actually proved by Xiangyang Wang and another author. They used the weak separation condition together with the totally disconnected. Yeah, that one is the key to the proof. Thank you very much.
All right, Ishan.
So you talked about self-embeddings between two different similar sets, but not about carpets. Have you thought about that?
There are actually some descriptions in Elgin and Hoffman's paper, but I believe they only describe something like when the carpet is of product form. And of course, I think this is very interesting to study, between different carpets instead of just consider the self-embedding case.
Further questions? For the online people, maybe?
Yeah, I have. So I vaguely remember that in our paper we also studied in the same paper these carpets and and there was some question that at a non-trivial intersection, or if you cannot, so there was some question there. It's very interesting that time. So is there any progress in that?
I actually can't forget that one. I have actually thought about a little bit. I think some of the questions are very, very interesting. Maybe we can have a discussion.
Okay.
Thank you.
More questions? Okay, if not, then let's thank JC again.